Hi, my name is Jamie Church. Today we're going to be talking about an example of a transcription essay with up elements. This video was made for MCDB 427 Molecular Biology at the University of Michigan. Enjoy! Let's start with a general reminder about RNA polymerase and gene transcription in prokaryotes. Now remember that RNA polymerase is made up of several subunits, with the core protein being made up of the beta prime, the beta, and the alpha subunits. So depicted here in blue in the little diagram is the sigma subunit. It has the capacity to bind to DNA by itself, but it does so very poorly. When it is bound to the core protein, the entire complex has improved binding capacity. And remember, the more we can improve the binding, the more transcription will occur. When it comes to gene transcription in prokaryotes, remember there's the -10 and -35 sites upstream of the +1 site, or the open reading frame. Now RNA polymerase is going to come in and it's going to bind to these sites and then transcription will occur. So what is an up element? Well, we're still going to have the -10 and -35 sites upstream of the +1, but we're also going to have this AT-rich region between the -40 and the -60 sites, that is the up element. Now the up element, it interacts with the alpha subunit of RNA polymerase. Now the alpha subunit of RNA polymerase is really subunits with an N-terminal domain and a C-terminal domain. It's the C-terminal domain that interacts with the up element. Now normally upstream of the +1 we have the -10 and -35 regions, but with an up element there's a third place for RNA polymerase to bind. Having 3 binding sites over 2 increases the likelihood that RNA polymerase would bind and transcription would occur. Math. So now we know what an up element is, and we know it interacts with the C-terminal domain of the alpha subunit of RNA polymerase. But this had to be discovered by someone. So let's talk about the experiment for how they got this information. The experiment. Really, it's an in vitro assay. The first thing they did is they had a vector, or a plasmid if you prefer, and they would insert a promoter with or without an up element and see how transcription varied. So this is the experimental setup. There's 3 things they're testing. You can see that they all have this hairpin loop structure at the end. This is a strong terminator. This makes sure that all transcription ends at the same point. So these 3 lines represent 3 different in vitro assays. The top one, marked 88, has the promoter and the up element. In the second in vitro assay, what they did is they removed all the DNA information from the -40 site to the -88 site, removing the up element. The third thing they did is they removed all the information again from the -41 site to the 88 site, but this time they subbed in random bases. So in all 3 cases, RNA polymerase would be added with the appropriate nucleotides so that RNA transcription could occur. This transcript was collected and then they ran it in a gel. For their experiment, they did everything in biological duplicates. So the promoter they chose to insert into the vector was the RRNB promoter. This naturally has an up element, making it a prime choice. Let's just quickly orient ourselves with gels again. Now remember, the smaller the item, in this case RNA, the faster it will travel through the gel, so the further down the gel it will be. Controls. Every experiment has them. These are the controls for this experiment. First, the vector. What this lane is showing you is the plasmid without any promoters being inserted. And we can see that transcription is occurring based on these bands here. This makes sense because we know at a minimum every plasmid must at least have an origin of replication and a selectable marker. The second is the LAC-V5 promoter. What these lanes are showing you is what happens when we insert a promoter into the vector. You can see that does not disrupt the function of the original transcripts. We can also get transcription by that promoter. See this box here. So now for the experiment, what we want to compare and contrast are these bands right here. These bands were created by the RRNB promoter. So looking at the 88 lane, that's with the up element and the promoter, we get these nice dark bands showing that a lot of transcription occurred. Now when we compare those to the bands from the 41 or the sub, they're much lighter in comparison, revealing that less transcription is occurring. The difference between both of those compared to the 88 is that they don't have the up element. Now in all 3 lanes we still have the -10 and -35 regions for RNA polymerase to bind. That's why there's transcription in all 3 lanes. But in the -88 lane we also have the up element. That's a third binding site for RNA polymerase. The more binding sites increases the likelihood that RNA polymerase is going to bind and more transcription is going to occur. So there's one more kind of cool thing I want to point out about this gel. Look at these bands here and these bands. Look at lane 88. With the up element, you see how the band intensity in these lanes is weaker? Well, this makes sense. There's only so much RNA polymerase available, and with the up element for lane 88, RNA polymerase is going to disproportionately bind to that versus the other promoters in the vector. Cool. So at this point, they know that the up element will increase transcription, but they don't yet know what part of the RNA polymerase is interacting with the up element. That leads us to the second experiment. In the second experiment, they kind of set up the exact same way as the first experiment, except when they add RNA polymerase, this time they have removed the C-terminal domain. Since this experiment was set up in pretty much the exact same way as the first one, let's just focus in on the experimental bands, knowing the controls will be the exact same as the previous figure. So it's easy to see that the band intensities are all very similar. What this experiment was showing us is that when we remove the C-terminal domain of alpha, even if an up element is present, the transcription levels are going to be equivalent to as if the up element wasn't present. There's just one more thing I want to bring your attention to about this experiment. It's going to really help if I have both gels side by side. Now the one on the left is the one where we have the C-terminal domain, and the one on the right is where we removed it. Otherwise, the experiments are the exact same. Is there anything kind of glaring at you as weird? Yes, exactly. All this RNA transcript just disappears from the second gel. That would lead us to the conclusion that the C-terminal domain is important for that promoter, and when we remove it, transcription just won't occur. So this is a pretty cool experiment, but it does have some limitations. Remember, this is a transcription assay. It can't actually say that the C-terminal domain of alpha is binding to the up element. What we can say is, when we have an up element and when we have the C-terminal domain of alpha, we see increased levels of transcription. So thank you for watching. I hope this video helped you get a better understanding of how transcription assays work, how you can read gels of transcription assays, and how the up element interacts with the C-terminal domain of alpha. As always, go blue.